In the shadowy fringes of our solar system, beyond the orbit of Neptune, lies a mystery that has puzzled astronomers for over a century: the elusive Planet X. A world that may have been hiding in plain sight, its existence inferred through tantalizing gravitational anomalies and the strange orbits of distant objects. Join us on a cosmic journey as we explore the relentless quest to uncover this hidden giant. A quest that challenges our understanding of the solar system and invites us to question what else remains undiscovered in the vast, dark reaches of space. This is not just the story of a planet. It's a tale of human curiosity, technological prowess, and the unquenchable thirst for exploration that drives us to the edges of the known universe and beyond. The concept of Planet X refers to a hypothetical planet located in the outer reaches of our solar system, beyond Neptune. This enigmatic world has been a subject of speculation and research for over a century, capturing the imagination of astronomers, scientists, and the public alike. The idea of Planet X arises from observations and mathematical predictions, suggesting irregularities in the orbits of known planets, particularly Uranus and Neptune, which hinted at the gravitational influence of an unseen celestial body. The search for Planet X is not just a quest for a new planetary member of our solar system, but also a profound journey into understanding the dynamics and evolution of the cosmos. Despite the technological advancements in telescopes and space exploration, Planet X remains elusive, embodying the mysteries of space that await discovery. The interest in Planet X extends beyond the scientific community, touching on themes of exploration, the unknown, and the limits of human knowledge. The story of Planet X is deeply rooted in the history of astronomy and the human pursuit of understanding the heavens. The concept dates back to the 19th century, following the discovery of Neptune in 1846. Neptune's discovery itself was a triumph of mathematical astronomy, as it was predicted based on irregularities in the orbit of Uranus. However, even with Neptune accounted for, some anomalies in the orbits of the outer planets remained unexplained, leading some astronomers to propose the existence of another planet beyond Neptune. In the early 20th century, the search for Planet X gained momentum under the auspices of Percival Lowell, an American astronomer who founded the Lowell Observatory in Flagstaff, Arizona. Lowell dedicated a significant portion of his career to searching for this mysterious planet, which he believed was responsible for the perceived discrepancies in the orbits of Uranus and Neptune. Although Lowell did not discover Planet X during his lifetime, his efforts laid the groundwork for future searches. The speculation about a ninth planet has evolved over the years, influenced by new discoveries and advances in technology. The discovery of Pluto in 1930 by Clyde Tombaugh, initially hailed as the long-sought Planet X, temporarily satisfied the quest. However, as further observations revealed Pluto's relatively small size and mass, it became clear that it could not account for the orbital perturbations of the outer planets, reigniting the search for a true Planet X. Over the decades, the hypothesis of Planet X has been reshaped by the discovery of the Kuiper Belt and other trans-Neptunian objects, expanding our understanding of the solar system's outer regions. The demotion of Pluto to a dwarf planet in 2006 by the International Astronomical Union further complicated the narrative, leaving the door open for a new Planet X to claim the title of the ninth planet. The journey to find Planet X embodies the ever-evolving nature of scientific inquiry, highlighting the interplay between theory, observation, and the relentless human desire to explore the unknown. As we continue to probe the depths of space with more sophisticated instruments and missions, the mystery of Planet X remains a captivating chapter in the ongoing saga of our solar system's exploration. The quest for Planet X is deeply rooted in the science of gravitational anomalies, which play a pivotal role in the cosmic detective work of astronomy. Gravitational anomalies are deviations from the expected gravitational field in space, often hinting at the presence of unseen masses exerting their influence. This principle has been a cornerstone in the discovery of celestial bodies since the 19th century, when the perturbations in Uranus's orbit led to the prediction and subsequent discovery of Neptune, showcasing the predictive power of Newtonian mechanics applied to celestial dynamics. In the context of Planet X, astronomers and theoretical physicists use similar methods to infer the existence of an unseen planet. By meticulously analyzing the orbits of known objects in the Kuiper Belt and beyond, scientists look for inconsistencies that cannot be explained by the gravitational pull of the known planets. These anomalies suggest the presence of a massive object whose gravity is sculpting the outer solar system's architecture, influencing the orbits of distant objects in a predictable manner that can be modeled and observed. Perturbations in the orbits of known planets and trans-Neptunian objects, TNOs, serve as potential indicators of Planet X's influence. The concept hinges on the observation that the gravitational forces exerted by all the planets in the solar system affect each other's orbits. When astronomers observe deviations from the expected paths, especially in the outer solar system, where objects are more sparsely located and less influenced by the Sun and the inner planets, they can infer the presence of additional gravitational forces at work. This line of inquiry gained significant momentum with the detailed study of the orbits of objects in the Kuiper Belt, a region of space beyond Neptune filled with icy bodies and dwarf planets. Certain clustering patterns and unusual orbits among these objects suggest they are being shepherded by a significant unseen gravitational source. These observations fuel the hypothesis that Planet X, a planet much larger than Earth, could be lurking unseen in the distant shadows of our solar system, its presence betrayed only by the subtle gravitational dance it orchestrates among the objects it influences. The explosion of exoplanet discoveries in the last few decades has revolutionized our understanding of planetary systems and has significant implications for the search for Planet X. The methods developed to find planets around other stars, such as the transit method and radial velocity method, have not only expanded our catalog of known planets beyond our solar system, but have also refined our techniques for detecting faint and distant objects within our own solar system. These discoveries have shown that planetary systems can be incredibly diverse and that large planets can exist in wide orbits around their stars, lending credence to the possibility of a Planet X-type object in our own backyard. The variety of exoplanet configurations observed, including those in highly elliptical or distant orbits, mirrors the theoretical predictions for Planet X and demonstrates that such an object's existence is plausible, given what we now understand about planetary formation and dynamics. Furthermore, the study of exoplanets has enhanced our tools and models for understanding gravitational interactions and orbital dynamics in multi-body systems. This progress, in turn, aids in the ongoing search for Planet X by allowing for more precise predictions about where such a planet might be found, its potential orbit, and how it would interact with the known objects in the solar system. The search for Planet X, therefore, stands at the crossroads of classical celestial mechanics and cutting-edge astrophysical research. It embodies the quest to understand our place in the universe, pushing the boundaries of detection technologies and theoretical models to uncover the secrets that our solar system may still be hiding. The Kuiper Belt and the Oort cloud are two critical regions in our solar system that provide observational evidence potentially pointing towards the existence of Planet X. The Kuiper Belt, a vast ring of icy bodies, including dwarf planets like Pluto, orbits the Sun beyond Neptune. The dynamics within this belt, such as the unusual orbits of some of its objects, hint at the gravitational influence of an unseen planet. These objects, known as extreme trans-Neptunian objects, ETNOs, have orbits that are highly elongated and point in similar directions, an anomaly that is difficult to explain without the presence of a massive, distant planet. Similarly, the Oort cloud, a theoretical cloud of icy objects surrounding our solar system at a distance of up to a light-year from the Sun, may also hold clues. While direct observation of the Oort cloud is beyond current technological capabilities, the trajectories of long-period comets originating from this region suggest the influence of a large object's gravity, further supporting the Planet X hypothesis. One of the most compelling pieces of evidence for Planet X comes from the unexplained gravitational influences on distant objects in the solar system. Astronomers have observed several instances where the orbits of objects in the outer solar system cannot be fully explained by the gravitational pull of the known planets. This includes the aforementioned ET nose, whose orbits suggest they are being shepherded by a massive unseen object. Additionally, some bodies in the Kuiper Belt exhibit clustering in their orbits that points to perturbations caused by a large object. These clusters are not random. Their orbits align in a way that suggests a gravitational relationship with a distant, massive entity, indirectly indicating the presence of Planet X. Infrared astronomy has become a vital tool in the search for Planet X, as it allows astronomers to detect objects that are too cold and distant to be seen in visible light. Celestial bodies that are far from the sun do not reflect much sunlight, making them incredibly dim and difficult to observe with traditional optical telescopes. However, even the coldest objects emit heat in the form of infrared radiation, which can be detected with sensitive infrared telescopes. The significance of infrared observations in the search for Planet X was highlighted by discoveries such as the dwarf planet Eris, which was found using images taken by an infrared camera. This technique could potentially uncover Planet X, as the planet is believed to be too distant and cold to be seen in visible light, but would still emit enough infrared radiation to be detectable with current technology. Projects like the Wide Field Infrared Survey Explorer, WISE, and its subsequent mission, NEOWISE, have scanned the sky for objects that could be Planet X. While these missions have not yet found definitive evidence of Planet X, they have discovered thousands of new celestial bodies, demonstrating the power of infrared observations in exploring the outer reaches of our solar system. The use of infrared astronomy, combined with the study of the dynamics of the Kuiper Belt and Oort cloud, and the analysis of unexplained gravitational influences, forms a comprehensive approach to searching for Planet X. Each piece of observational evidence adds to our understanding of the outer solar system and brings us closer to potentially discovering this elusive planet. The search for Planet X has a rich history beginning in the early 20th century with astronomers like Percival Lowell, who believed that perturbations in the orbits of Uranus and Neptune were evidence of a ninth planet. Although Lowell's efforts did not lead to the discovery of Planet X, they paved the way for future searches and led to the discovery of Pluto in 1930, which was initially considered to be the elusive Planet X, until further observations showed it was too small to account for the observed gravitational effects. In the late 20th and early 21st centuries, the search for Planet X evolved with advances in technology and the discovery of the Kuiper Belt. This region beyond Neptune is populated with small, icy bodies, and observations of their orbits have provided new evidence for Planet X. For instance, the discovery of Eris in 2005, a dwarf planet that is one of the largest known objects in the Kuiper Belt, reignited interest in the search for other distant objects in our solar system. Current searches for Planet X are more sophisticated, utilizing the latest in telescope technology and computational models to scan the outer reaches of the solar system. Projects like the Subaru Telescope's Hyper-Suprime Cam survey have the capability to detect faint objects far beyond the orbit of Neptune, offering hope that Planet X could be discovered if it exists. The advancement of telescopic technology has significantly impacted the ability to detect distant objects in our solar system. High-resolution imaging, adaptive optics, and infrared sensing are among the technologies that have enhanced the search for Planet X. These technologies allow astronomers to observe objects that are too faint or too far away to be seen with older instruments. For example, the use of infrared telescopes, as mentioned earlier, is critical in detecting the heat signatures of cold, distant objects that are not visible in the optical spectrum. The James Webb Space Telescope, JWST, with its powerful infrared capabilities, is expected to play a significant role in exploring the outer solar system and could potentially uncover evidence of Planet X. Additionally, the use of wide-field surveys, which can scan large areas of the sky quickly, increases the chances of detecting moving objects in the far reaches of the solar system. The Vera C. Rubin Observatory, once operational, is anticipated to revolutionize our understanding of the outer solar system with its Large Synoptic Survey Telescope, LSST, capable of capturing extremely faint objects across the night sky. Citizen science initiatives have become an invaluable part of the search for Planet X, allowing amateur astronomers and enthusiasts to contribute to scientific discovery. Projects like Zooniverse's Backyard Worlds, Planet 9 Inches invite the public to sift through astronomical data to help identify potential candidates for Planet X and other unknown objects in the solar system. These initiatives leverage the power of crowdsourcing to analyze vast amounts of data generated by telescopic surveys. Volunteers review images and look for moving objects that could indicate the presence of a previously unidentified planet or dwarf planet. Notable successes of citizen science in astronomy include the discovery of several brown dwarfs, demonstrating the effectiveness of public engagement in scientific research. The contribution of citizen science to the search for Planet X underscores the democratization of space exploration. By involving a wide audience in the search, not only does it increase the manpower behind the effort, but it also raises public interest and awareness of space science, fostering a sense of collective investment in unraveling the mysteries of our solar system. The hypothetical Planet X, if it exists, is speculated to be a giant planet with a mass significantly greater than Earth's, potentially making it the fifth largest planet in our solar system, after Jupiter, Saturn, Uranus, and Neptune. Estimates of its size and mass vary, but most theories suggest it could be anywhere from 2 to 10 times the Earth's mass. This size range is based on the gravitational effects needed to explain the observed anomalies in the orbits of distant Kuiper Belt objects. In terms of composition, Planet X is thought to be a gas giant, or an icy giant, similar to Uranus and Neptune. Its composition would likely include hydrogen, helium, water, ammonia, and methane, with a possible rocky or metallic core. Given its presumed distance from the Sun, it would be an extremely cold world, with surface, or cloud top, temperatures potentially falling below -200 degrees Celsius. The orbit of Planet X is one of the most intriguing aspects of its existence, with speculations suggesting it has a highly elliptical, distant orbit around the Sun. Estimates suggest that it could take between 10,000 and 20,000 Earth years to complete one orbit, indicating it could be currently located far beyond the known planets, possibly as far as 200 to 800 astronomical units, AU, from the Sun. 1 AU is the distance from the Earth to the Sun. One theory proposes that Planet X may be in a gravitational dance with other objects in the solar system, possibly in orbital resonance with a group of trans-Neptunian objects. This means that Planet X and these objects would have orbital periods that are simple fractions of each other, a relationship that can stabilize the orbits within this distant and crowded field of icy bodies and dwarf planets. The existence of Planet X could have profound implications for the dynamics of the solar system. Firstly, its gravity would influence the orbits of objects in the Kuiper Belt, and possibly even closer to the Sun, contributing to the unique orbital characteristics observed in some trans-Neptunian objects. This could help explain the clustering of orbits in the Kuiper Belt and the existence of objects like Sedna with extremely elongated orbits. Moreover, Planet X could also play a role in the distribution and characteristics of comets entering the inner solar system. Its gravitational pull could deflect comets from the Oort cloud or the distant Kuiper Belt into orbits that bring them closer to the Sun, possibly impacting the frequency and trajectory of cometary visits to the inner solar system. Finally, the discovery of Planet X would necessitate a re-evaluation of our understanding of solar system formation and evolution. The presence of such a large object in a distant orbit could provide new insights into the processes that shaped the early solar system and the dynamics of planet formation, possibly offering clues about the distribution of similar objects around other stars. The search for Planet X has not been without its controversies and skepticism. One of the primary criticisms is the lack of direct observational evidence of such a planet, despite extensive searches using advanced telescopes and detection methods. Critics argue that the gravitational influences attributed to Planet X could be the result of observational biases, errors in data interpretation, or a misunderstanding of the dynamics of distant solar system objects. Additionally, some scientists question whether the mathematical models used to infer the existence of Planet X accurately represent the complexities of the solar system. They suggest that the observed anomalies in the orbits of trans-Neptunian objects could arise from collective gravitational effects of smaller, yet undiscovered bodies in the outer solar system, rather than a single massive planet. Several alternative explanations have been proposed to account for the observed anomalies in the outer solar system without invoking Planet X. One theory suggests that the clustering of orbits among some distant Kuiper Belt objects could result from the collective gravitational effects of these objects themselves, rather than an unseen planet. This could mean that the statistical significance of the orbital alignments may have been overestimated. Another hypothesis posits that the observed gravitational effects could be the result of a massive disk of small icy bodies in the outer solar system, exerting collective gravitational influences that mimic the presence of a larger planet. Additionally, some researchers have explored the possibility that interactions with passing stars or the galactic tide, the gravitational effect of the Milky Way, could perturb the orbits of distant solar system objects, leading to the observed anomalies. The debate over Planet X is a vibrant and ongoing part of scientific discourse, reflecting the dynamic nature of astronomical research. Proponents of the Planet X hypothesis argue that the peculiar orbital characteristics of certain trans-Neptunian objects are best explained by the presence of a distant massive planet. They continue to refine their models and search strategies, hoping that technological advancements will eventually lead to direct detection. On the other hand, skeptics emphasize the need for caution and rigorous scientific methodology, pointing out the potential for confirmation bias and the importance of considering alternative explanations. The scientific community remains divided, with some researchers dedicated to proving the existence of Planet X, while others focus on alternative models to explain the observed phenomena. The controversies and skepticism surrounding Planet X underscore the challenges of exploring the unknown frontiers of our solar system. They reflect the scientific process at work, where hypotheses are continuously tested, debated, and revised in the light of new evidence. Regardless of the outcome, the search for Planet X has spurred significant advancements in our understanding of the solar system's outer reaches and has highlighted the importance of keeping an open mind in the face of the unknown. The search for Planet X continues to be a driving force behind several upcoming astronomical missions and telescopic projects. These initiatives aim to extend our observational capabilities further into the outer solar system, increasing the chances of detecting Planet X or providing definitive evidence regarding its existence. One of the most anticipated projects is the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, which promises to revolutionize our understanding of the cosmos. With its wide-field survey telescope, LSST is expected to observe billions of galaxies and a vast number of solar system objects, including potential candidates for Planet X. Its ability to capture the entire sky repeatedly over a decade will be particularly useful in tracking the movement of distant objects and identifying anomalies suggestive of a massive planet's influence. The European Space Agency's ESA Euclid mission, primarily focused on dark matter and dark energy, will also contribute valuable data relevant to the search for Planet X. Its sensitive instruments are capable of detecting the faint light of extremely distant objects, potentially including those affected by Planet X's gravity. Furthermore, advances in space-based infrared astronomy, such as those expected from the James Webb Space Telescope, JWST, could significantly enhance our ability to detect Planet X. JWST's unparalleled infrared sensitivity makes it an ideal tool for observing the cold, distant objects that might orbit in the outer solar system. Technological advances in both ground-based and space-based astronomy are set to enhance our ability to detect and study distant celestial bodies significantly. Developments in adaptive optics, which compensate for the Earth's atmospheric turbulence, are improving the resolution and clarity of ground-based observations. This makes it possible to detect fainter objects and resolve finer details than ever before. In space, the next generation of infrared telescopes and high-precision astrometry missions will be able to detect the subtle signs of distant planets through their gravitational effects on nearby stars or the faint heat they emit. Additionally, improvements in data processing and analysis, powered by advances in artificial intelligence and machine learning, will enable the handling of the vast amounts of data these missions produce, increasing the efficiency of searches for objects like Planet X. The discovery of Planet X, or conclusive evidence of its absence, would have profound implications for our understanding of the solar system's formation and evolution. If Planet X exists, it would provide key insights into the processes of planetary formation, migration, and the dynamics of the outer solar system. It could reveal new information about the distribution of mass in the early solar system and the interactions between planets and smaller bodies. Conversely, if searches prove that Planet X does not exist, this outcome would also be significant. It would challenge current models of the solar system that predict its existence and force a re-evaluation of the theories explaining the observed anomalies in the orbits of distant solar system objects. This could lead to new understanding of the gravitational interactions at play in the outer solar system and refine our models of how solar systems evolve over time. Regardless of the outcome, the ongoing and future exploration and observation efforts are crucial steps in our quest to unravel the mysteries of the cosmos. They underscore the importance of continuous inquiry and technological innovation in expanding the boundaries of our knowledge. The quest for Planet X has been a compelling narrative in the field of astronomy, weaving together the threads of mathematical prediction, observational evidence, and technological advancement. The concept of Planet X emerged from observed gravitational anomalies in the orbits of Uranus and Neptune, suggesting the presence of an unseen planetary mass in the outer reaches of our solar system. Despite extensive searches, Planet X remains elusive, embodying the mysteries that lie beyond the current boundaries of our knowledge. The search has been driven by a combination of factors, including perturbations in the orbits of distant Kuiper Belt objects, unexplained gravitational influences, and the potential for infrared detection of cold, distant celestial bodies. Advanced telescopic technologies and citizen science initiatives have played significant roles in the ongoing efforts to discover Planet X, showcasing the evolution of astronomical research and the democratization of space exploration. The pursuit of Planet X is marked by uncertainties that underscore the complexity of our solar system and the challenges inherent in exploring its most distant regions. The debate over the existence of Planet X reflects the dynamic nature of scientific inquiry, where hypotheses are continually tested against observational evidence. Skepticism and alternative explanations for the observed anomalies serve as important reminders of the need for rigorous methodology and open-mindedness in scientific research. Regardless of the outcome, the search for Planet X is a testament to human curiosity and the drive to understand the universe, encouraging continuous exploration and questioning of accepted models. The implications of the search for Planet X extend far beyond the quest to find a single distant planet. This endeavor contributes to our broader understanding of planetary science, offering insights into the formation and evolution of our solar system. It challenges existing models and prompts the development of new theories that can accommodate the latest discoveries and observations. Whether Planet X is found or not, the research and debates surrounding it enrich our knowledge of planetary dynamics, the structure of the outer solar system, and the processes that govern the formation of celestial bodies. The exploration of these frontiers not only deepens our understanding of our own solar system, but also informs our study of exoplanets and planetary systems throughout the galaxy, highlighting the interconnectedness of astronomical research.